what we are going to learn in today's class is about damping. So before we start with damping, let's just discuss a very basic idea here. If you're considering a pendulum swinging to and fro, it's not that it's going to swing forever. Eventually, because of air resistances, and if you're applying some external kind of force, it's going to come to a stop. So even if you're not applying any force, because of the air resistance, it cannot go on forever and ever. That means the amplitude is going to slowly reduce, and that is what we call as damping. Now, let's imagine we have this box, let's say of mass m, and it is connected with a spring. Now, if you pull the box and let the displacement be in this direction, and that's x, we basically have a force, which is the spring force, which is acting in the opposite direction. But then, since it's inside water, there is also a viscous force which is acting on this. So if the velocity is in this direction, there is going to be a viscous force which will act in the opposite direction. Let's name it Fd, and D stands for the drag force. Now let's go to the very basic idea of Hooke's law, which we have done in few classes. And imagine we have got this box of mass m connected to a spring. Now, when the displacement is in this direction, the spring will try to pull it back in the opposite direction, and we basically have a force Fs, which is called the spring force. Now we have modified the system. What we did, we actually connected a small vane, and this can be called as a vane. So a vane may be, a rubber tube or something, okay, in the shape of a rubber, rectangular rubber, which is actually connected with the mass m via a string, and this particular vane is dipped in some liquid, maybe water, maybe glycerin, and maybe oil or something like that. Now, when I pull it, the spring will pull it back, and as it pulls it back, it gains some velocity. But this velocity will be less because of the drag force that is being offered by the water body. You can take a very simple example. Imagine you have got a bucket of water, and you have a mug, and you want to pull out the water out of the bucket. But when you do it, if the velocity is very high, the force with which you need to pull it out will be more. But if you're pulling it out slowly, you can easily take it out by applying lesser force. Now, why does that happen? Because if there is more velocity, the drag force, which is acting in the opposite direction, would be more. So in this situation, we have this Fd as the drag force, which is being offered to this mass m because of the vane which is dipped inside water. So for simplicity, this vane might be made up of rubber. So in this situation, we can see that in this setup, there are two forces which are acting. One is Fs, which we call as the spring force, and secondly, we have the drag force, which we denote as Fd. So these are the two forces which are acting on the system. Now our aim is to devise a mathematical formulation for the same. We know the forces, we know the situation, and now we want to understand this mathematically. So that's the aim for this particular topic. So if you consider the spring force, we can write it down as kx, and if we took into it vectorially, we can write down that the spring force is minus of kx. Why there is a minus sign? Because if the displacement is one direction, the drag or the spring force will be in the opposite direction. So the spring force is opposite to displacement, as we can see here, or you can imagine it. It's a very practical example. On the other hand, if we talk about the drag force, we have seen that the drag force will be more depending on what is the velocity with which you are pulling it out. So that means the drag force is directly proportional to the velocity. We need to replace it with a proportionality constant, and that would be, let's say, b. So this is b to v. Again, if you want to write it down in the vector form, you can say that the force is opposite to the direction of velocity. So that means in vectorial form, Fd is equal to minus b into v. Now this is the setup, and this is the idea that we have developed to devise a mathematical formulation for the same. Now, if you want to proceed ahead, what we have to see is the total force acting on the system. There are two forces, so that means the total force can be a sum of these two forces. So let's try to do this sum. And what we can do here is we can write down this as total force, or we can also call it as the resultant force. And let me just denote it with F, and I can write it down as a sum of the spring force and the drag force. Now, if we do that, we can replace these values, the vector values, and I can write it down as minus of kx and then minus bv. Now, what's the total force? It's obviously mass into acceleration, and we know that acceleration can be written as the double differentiation of the displacement. So let me just write it down as d2x dt square. So that's your total force is equal to, I can write it down as minus bv minus kx. So it will be minus of kx minus b into velocity. Velocity is rate of change of displacement. So I can just write it down as dx by dt. Let's bring all the terms on one side. So on this side, we can actually have it as m d2x dt square. And if I take the b term on the other side, it will be plus b dv, or sorry, it will be dx dx divided by dt. Let me take k on the other side, it will be plus kx is equal to 0. Now, this is a second order differential equation in x. In the next class, what we are going to do is we are going to simplify this further and we are going to solve it for x.